Welcome to this explainer. If you've ever stopped to watch heavy construction equipment in action, like, say, an excavator effortlessly tearing into the earth, or a massive crane hoisting steel beams way up into the sky, you have actually witnessed the sheer, unadulterated power of fluid in motion. It's pretty amazing. In this explainer, we're going to break down exactly how these giant machines harness something as simple as liquid to perform these incredible feats of strength, and we'll unpack the core components that make the whole shebang possible. It really is a captivating question, isn't it? I mean, how can a tiny little joystick movement inside a comfortable, air-conditioned cab effortlessly lift a 50-ton boulder? Without hydraulics, this kind of heavy lifting would be nearly impossible for humans relying purely on mechanical advantage and muscle. To put it all into perspective, older steam-powered machines could move the same amount of material in one day that would take two people with a wheelbarrow 2 entire weeks to complete. The secret to this monumental leap in capability is, for sure, hydraulic power. So, here is our roadmap for today. We'll be covering 1. Why use liquid power? 2. The reservoir, fluid storage. 3. Hydraulic pumps, generating flow. 4. Directional valves, traffic control. And finally, 5. Cylinders, the muscle. Let's dive right into Section 1, Why Use Liquid Power? The ultimate power transmitter. Now, you might be wondering why heavy equipment relies on hydraulics instead of purely electrical, mechanical, or pneumatic systems. Well, the main reason comes down to power and reliability. Hydraulic systems can lift much heavier loads with significantly greater force, and by relying on fluid, they actually use way fewer moving parts compared to complex systems of gears or pulleys, which greatly reduces the chances of mechanical breakdowns and everyday wear and tear. But the absolute biggest advantage? With hydraulics, you can lift heavy loads at a steady rate of power and torque. Other mechanical systems often struggle with this. They lose power when speed increases. Hydraulics give you that consistent, brute strength that's perfectly suited for heavy-duty tasks. And this brilliantly illustrates the foundational science behind it all, Pascal's law. Because hydraulic fluid, which is typically a specialized oil, is an incompressible liquid, it acts as a perfect medium to multiply force. If you apply pressure to this fluid inside a closed circuit, that pressure is transmitted equally everywhere and in all directions. It doesn't shrink, it doesn't compress like a gas would. Instead, that applied force transfers directly to the other end of the system, moving large pistons to handle tasks that require massive, massive power. Moving on to Section 2, the reservoir, fluid storage. You can think of this as the stomach and lungs of the system. The reservoir is so much more than just a simple metal box holding oil. When it comes to reservoir design, bigger isn't always better. Actually, modern trends favor smaller, highly efficient reservoirs. Inside, you'll find physical barriers called baffle plates, and these separate the hot, agitated fluid entering the tank from the calmer fluid about to be drawn back into the pump. There are also strainers, drains, and air breathers on top. It's a busy place. So the crucial takeaway here is that the reservoir performs multiple vital functions to keep the hydraulic anatomy totally healthy. Yes, it obviously holds enough fluid to supply the system's varying needs, but it also provides a large surface area to transfer heat and cool the fluid down. It gives returning, high-velocity fluid time to slow down, which allows heavier dirt and contaminants to safely settle to the bottom and lets trapped air bubbles escape to the top. It even accommodates the natural thermal expansion of the fluid as the machine gets hot. It is a highly engineered environment for sure. Let's look at Section 3, hydraulic pumps generating flow. This is the beating heart of the machine. Before we dive into the mechanics, we need to bust a very common myth right here and now. Pumps pull fluid and create flow, not pressure. A pump's only job is to draw mechanical power, usually from a combustion engine or an electric motor, and transfer it into hydraulic power by spinning the fluid and delivering it into the system. The pressure is actually created by the resistance to that flow further down the line. If there was no resistance, the oil would just flow out into nothingness with zero pressure. Take a fixed displacement gear pump, for example. In these, every single revolution delivers the exact same amount of oil. As the gears spin, they come out of mesh on the inlet side, expanding the volume and creating a suction that draws fluid in from the tank. The fluid is then carried around the outside of the gears, and when the teeth mesh back together on the discharge side, the volume decreases, positively ejecting the fluid out into the high-pressure system. It's this continuous, powerful cycle of grabbing and pushing oil. Section 4, directional valves, traffic control. We like to call this the brain of the circuit. Inside a standard four-way valve is a precision-machined spool. In phase 1, the neutral position, springs keep the spool centered, blocking all ports. Nothing moves. But when the operator moves a joystick, the spool shifts. Shifting left in phase 2 opens a path from the pressure port, or port P, to working port A, sending fluid out to an actuator. Shifting right in phase 3 directs that pressure to port B instead, while allowing fluid from port A to return to the tank. This simple spool shift is literally how an operator controls the exact movement of a massive machine. It's like a smart traffic cop routing cars. And because hydraulic systems can operate at extremely high pressures, they absolutely require strict safety measures. That's the job of the relief valve. If the pressure in the system spikes dangerously high, it overcomes a calibrated spring inside the relief valve. A poppet opens up, and the highly pressurized fluid is safely diverted right back to the tank. This prevents catastrophic damage to the pump or the rest of the machinery. It's a crucial safety net. Finally, Section 5. Cylinders, the muscle. This is where we convert all that pressure into linear force. A hydraulic cylinder basically consists of a barrel, a piston, and a heavy-duty chrome rod. Pressurized fluid enters through a port and pushes directly against the face of the piston. That pressure forces the rod to extend outward, performing the actual work, whether that's lifting a dump truck bed or pushing a massive load of dirt. When fluid is allowed to drain, the cylinder retracts. This happens either by gravity, a spring, or by pumping fluid into the opposite side of the piston in what's called a double-acting cylinder. Now here is a fascinating physical reality of hydraulic design. Cylinders actually have different strengths depending on the direction they are moving. If you pump oil into the barrel end, or cap end, the fluid pushes against the entire surface area of the piston, giving you maximum pushing force. But if you pump fluid into the rod end to pull something, the physical rod itself is taking up space inside the cylinder. Because there is less surface area for the fluid to push against, the cylinder generates significantly less pulling force, even if the fluid pressure is exactly the same. Wild, right? So engineers use this mechanical advantage to their benefit when designing construction equipment. Machines are built to use the powerful barrel end to do the absolute hardest work, like an excavator lifting a heavy bucket full of rock against the forces of gravity. Conversely, the weaker rod end is used for tasks where gravity is already helping out, like lowering that same bucket back to the ground. Mechanics even use this difference to diagnose equipment. If you pressurize both sides of a cylinder equally, the rod will actually begin to extend because the barrel end has that built-in mechanical advantage. If that happens unexpectedly, it tells a mechanic there is an internal leak. So, we followed the power of fluid from a quiet reservoir through the beating heart of a pump, routed by the brain of a valve, all the way to the raw muscle of a cylinder. It is a brilliant synergy of engineering, but it leaves us with a provocative thought. As technology merges with fluid power and we introduce advanced digital and electronic controls to these mechanical beasts, what impossible feats of engineering will hydraulic power unlock next? The potential is truly limitless. Thank you for joining me on This Explainer, and keep exploring the amazing mechanics of the world around you.